Hello students, today we will see the next concept in the physical layer, that is a transmission of digital signal. We can transmit a digital signal by using two ways, that means baseband transmission and broadband transmissions by using the modulations. Then first type is baseband transmission. Baseband transmission means sending a digital signal over a channel without changing the digital signal to analog signal. That means here we cannot change the digital signal to analog signal, directly passes the signal. These baseband transmissions requires low pass channel, a channel with a bandwidth that starts from the 0. So the baseband transmission has two cases. Then first is a low pass channel with wide bandwidth, and second is low pass channel with limited bandwidth. That means this is the actually baseband transmission requires low pass channel. So it having two types of the baseband transmissions, like wide bandwidth and limited bandwidth. Here see the diagram. So this is the digital signal and this is the channel. Here baseband transmission means sending the digital signal over the channel, but here the difference is that changing the without changing the digital signal to the analog signal, it directly passes the signal without any changes. Then first type is low pass channel with a wide bandwidth. If you want to preserve the exact form of the non-periodic digital signal with vertical segment and horizontal segments, we need to send the entire spectrum, the continuous range of the frequencies between 0 and infinity. Here this is possible when if we have the dedicated medium with an infinite bandwidth between the sender and receiver, that preserve the exact amplitude of each components of the composite signal. Thus here the baseband transmission of the digital signal that preserve the shape of digital signal, which is possible only if we have a low pass channel with an infinite or very wide bandwidth. Then second is a low pass channel with limited bandwidth. In the low pass channel with limited bandwidth, we approximate the digital signal with an analog signal. Here the level of approximations depends on the bandwidth available. The required bandwidth is proportional to the bit rate. Then if you need to send bit faster, we need more bandwidth. Here the baseband system extend only to limited distance because the higher frequencies at attenuations of the signal, here it is the most pronounced, and pulses blur out because it causing the large distance communication totally impracticable. Here the low pass channels with the wide bandwidth and with limited bandwidth. First is wide bandwidth. That means here we passes the infinite bandwidth between sender and receiver. But in the case of limited bandwidth, we send the approximate digital signal with an analog signal. Then second concept is broadband transmission. Broadband transmissions or modulations means changing the digital signal to an analog signal for transmission. We already seen in the baseband transmission we cannot change the signal, but here difference is that in broadband transmissions we can changing the digital signal to an analog signal for transmission. Here the modulations allows us to use the band pass channel. Here a difference is that when we modulations this the broadband transmission, we use the band pass channel, and the bandwidth of the band pass channel does not start from 0. But in the case of baseband transmission, we can start the bandwidth of the channel from 0. This is the type of channel is more available than a low pass channel. See, this is the figure. Here the workstation, here is a modem. It is modulated here first. This is the digital signal and this is the analog signal. Here this is baseband and here broadband. If the available channel in is the baseband channel, here this is the baseband channel. If suppose consider, and we cannot send the digital signal directly to the channel in case of the baseband signal, but we need to convert the digital signal to an analog signal before the transmission. Here this is the difference in the broadband transmissions. When we send band pass channels, we cannot send the digital signal directly to the channel because of we need to convert the digital signal to analog signal before the transmissions. That means when we send the signal before, we can convert this signal digital into the analog signal and then transmissions is possible. Then next is transmission impairments. When a signal is transmitted over a communication channel, it is subjected to different types of impairments because of the imperfect characteristics of the channel. As the consequences, the received and transmitted signals are not exactly same. Then outcome of the impairments are manifested in two different ways in the like analog and digital signal. These impairments introduce random modifications in analog signal leading to distortions. On the other hand, in case of digital signal, the impairments lead to error in the bit values. Then impairments of the signal means that signal quality at the beginning of the medium is not the same at the end of the signal here that means when the first signal quality becomes very high, but at the end this is not the same. That's why here the impairments occurs, and the impairments can be broadly categorized into the following three types as shown in this figure. See, this is the figure. Impairment causes attenuation, distortion and noise. These are the three impairments can be categorized. First, then we will see one by one. First is attenuation. Attenuation means a loss of energy, the resistance of the medium. When a signal travels through a medium, it loses some of the energy in the overcoming the resistance of medium. The irrespective of whether a medium is guided or unguided, the strength of the signal falls off with the distance. In case of guided media, the attenuation is logarithmic. Then whereas in case of unguided media, it is more complex function of the distance and the material that constitute the medium. To compensate the loss of signal, amplifiers are used to amplify the signal. Figure shows the effect of attenuation and amplifications. Show this is the figures for attenuation. Here first is this is the original signal in the point first. When transmission medium, this attenuation at the point 2, it will be, this is the small image. That means this attenuations is occurred. Here the when we send this signal at it loses the some energy, so it overcome the resistance of the medium. And then when we solve this problem, we connect the amplifier and then our signal in original positions, and then to show that signal has lost and gained strength until it decibel is used. Here dB stands for decibel, and P1 and P2 are the two powers of the signal at point 1 and point 2 respectively. Then attenuation in dB is dB is equal to suppose 10 log to 10 P2 upon P1, where the P1 and P2 are the power of the signal at the point first and second respectively. The decibel is negative if the signal is attenuated and positive if the signal is amplified. Then second one is distortion. Distortion is the alternations of signal due to the differing propagation speed of each of the frequencies that make up the signal, and the signal changes its forms or shape, and distortions can occur in composite signal made of the different frequencies. Here each signal component has its own propagation speed through a medium and therefore its own delay in arriving at the destinations. Here the signal components at the receiver have phases like different from what they had at the sender, so that the shape of composite signals is not the same. Show the effect of the distortion on a composite signal. See, this is the figure. The composite signal sent, and then the component in the phases at the sender side, but at the receiver side this is the composite signal received and component of the phases. Here it shows the effect of distortion on a composite signal. Then third one is noise. Noise is the external energy that corrupts a signal. A signal is transmitted through a channel. Undesired signal in the form of noise get mixed up with a signal, analog with distortion introduced by the transmission media. Here the noise can be categorized in the following four types. First one is the thermal noise. The thermal noise is the random motion of the electron in a wire which creates an extra signal not sent by the transmitter. It is also called as the white noise. Then second is induced noise, created by the motor or the appliances, and these devices act as a sending antenna and the transmission medium acts as a receiving antenna. Then third is crosstalk. Crosstalk is a result of the bunching several conductors together in a single cable, and the signal carrying wires generate electromagnetic radiations which is induced on the other conductor because of the close proximity of the conductor. While using telephone, it is a common experience to hear conversation of other peoples in the background. This is known as the crosstalk. We have already experienced the crosstalk telephone conversion. And the impulse noise last is then impulse noise is a irregular pulses or the noise spike of a short duration generated by phenomena like lightning, spark, due to the loose contact in electrical circuits, etc. Impulse noise is a primary source of bit errors in digital data communication. This kind of noise introduce the burst errors. Then data rate limits. In data communications, a very important consideration is how fast we can send data in bits per second over a channel. Data rate depends upon the bandwidth available, then the level of the signal we use, and third is the quality of the channel, that means the level of noise. The maximum rate at which data can be correctly communicated over a channel in the presence of noise and distortion is known as its channel capacity. The two formulas were developed to calculate the data rate. One by the Nyquist for a noiseless channel, and another is a Shannon for a noisy channel. Then first is Nyquist bit rate formula for noiseless channel. For a noiseless channel, the Nyquist bit rate formula defines the theoretical maximum bit rate. Here bit rate is equal to 2 into bandwidth into log 2L, and bandwidth is a bandwidth of the channel. L is used for it is the number of signal levels used to represent the data, and bit rate is a bit rate in bits per second, that means BPS. Here one of the example, consider a noiseless channel with a bandwidth of 3000 Hz transmitting a signal with two signal levels. That means the maximum bit rate can be calculated. Here given information is like the here bandwidth is given. Then second is here also gives the signal level, here the two signal levels, and the we have calculate the maximum bit rate. In this data rate limits we have already seen, this is the formula. Bit rate is equal to 2 into bandwidth into log 2L. Just put up the given information. Here bit rate is equal to 2 into bandwidth is 3000 hertz into log 2, and L stands for the signal levels, and here we give the we have provided the information 2 levels, so log 2 to 2, L's value is 2. When we calculate this, here log 2 2, that means 1, and here 2 into 3000 is equal to 6000 bps. Then second example, consider the same noiseless channel transmitting a signal with 4 signal levels. Here the 4 signal level, for each level we send 2 bits, and the maximum bit rate can be calculated. The given information is 4 level, that means L is equal to 4, and here the we have provided the we send 2 bits, and this can be calculated. It also noiseless, it same noiseless channels, that means here also providing the bandwidth is 3000 hertz, and put the formula bit rate is equal to 2 into bandwidth into log 2L. This is the formula, and put up 2. Then here bandwidth is provided in previous example 3000 hertz, and then log 2 4. When we calculate this, here the log 2 2, this is the 2, and 2 into here 3000, 6000, and 6000 into 2, that means 12,000 bps, bits per second. Then also another example is, we need to send the 265 kbps over a noiseless channel with a bandwidth of the 20 kilohertz. Then how many signal levels do we need? Here we can use the Nyquist formula as shown in the as shown in below. There the formula is bit rate is equal to 2 into bandwidth into log 2L. But here we provide the bit rate. Then second is here the 265 kbps, it provide the here bit rate. Then also provide the 20 kilohertz bandwidth and log 2L. Here we find out L. Then L is equal to, when we this calculate, L is equal to 6.625, that means 2 raised to 6.625, and here 98.7 levels. Since the result is not a power of 2, we need to either increase the number of levels or the reduce the bit rate. If we have 128 levels, the bit rate is 280 kbps, and if you have 64 levels, the bit rate is 240 kbps. Then Shannon's law for noisy channel. In reality, we cannot have a noiseless channel. The channel is always noisy. When there is noise present in a medium, the limitations of both bandwidth and noise must be considered. A noise spike may causes a given level of the interpreted as a signal of the greater level. Then if it is in positive phase or the smaller level, if it is negative phase, noise becomes more problematic as the number of the levels increases. Then Shannon's capacity formula. Capacity is equal to bandwidth into log 2 in 1 plus SNR. Here the then bandwidth is formula of the channel. Then the capacity is the capacity of channel in bits per second, and SNR for the signal to noise ratio, SNR signal noise and ratio, and it is calculated as SNR is equal to average signal power upon average noise power. Then SNR in dB is calculated as SNR dB is equal to 10 log to 10 SNR. Here the example for the Shannon's law. Here we can calculate the theoretical highest bit rate of the regular telephone line. A telephone line normally has the bandwidth, suppose here given the information 3000 Hz, and assigned for the data communication, and the signal to noise ratio, that means SNR, is 3162. For this channel capacities and calculate the channel capacity, we have provided the formula. Capacity is equal to bandwidth into log to 1 plus SNR, and here put the values. Capacity is equal to B log 2 plus SNR is equal to, here the bandwidth is 3000 Hz, log 2 and 1 plus, here the SNR, here the Shannon's noise ratio is 3162, so here 3162. When we calculate this, we get the answer 34,860 bps. This means that the highest bit rate of telephone line is 34.860. Here the BPS, like the kbps. If you want to send data faster than this, we can either increase the bandwidth of the line or improve the signal to noise ratio.